Welcome to Introduction to Contrast Injectors. My name is Steve Maull. I'll be your presenter for the next hour. Basically, this is like a 1 hour version of a normally like a 2.5 or 3 hour class. So there's stuff that gets squashed down. We're not gonna do the howdy do's like I normally do in the morning. But before we get into this, who here doesn't know anything about imaging or how an image is produced? It's fine, you don't have to know, but anybody? All right, so we're all aware, all right? So I can dumb this down a little bit more. Your typical image, all right, is think of a normal X-ray. Chest X-ray, got a patient on the table, and then normally there's an X-ray tube above the table, and then some image capturing device. It used to be film, now it's the digital plate is inside or underneath the table, all right? Fire the X-rays into the patient, it produces an image, okay? Now, one thing about how an X-ray is produced, all right? Those X-rays that went into the patient, those X-rays are either going to penetrate the patient and hit the plate, or they're going to be absorbed by the patient and not get to the plate. All right, so we have penetration and absorption. Now, to get a good X-ray image, we need both things to happen. Okay, we need some of that radiation to get absorbed by the patient, and we need some of it to pass through the patient and strike the plate. Now, the reason for that is when X-rays strike that imaging plate, it turns those parts of the image darker. All right, the parts of the imaging plate that don't get struck by radiation, those parts of the plate stay lighter. Now, if you think about it, if all the radiation we fired into the patient were absorbed by the patient, that means no X-rays hit the plate. That means a completely clear white image. The opposite happens if all the X-rays we fired into the patient penetrated through the patient, the entire plate got hit. Now that's just as bad as this an all black image now, right? To get those bone structure to show up on the image, we need penetration and absorption. Now, the odds that an X-ray photon will penetrate a body part is determined by the thickness and the density of the body part. The thicker and denser it is, the more likely that bone is going to absorb the X-ray. The less thick and dense, the more likely the X-ray photon will pass through and strike the plate and turn that area darker. So that's why if you think a normal image of an X-ray, like a chest where all the bones are white and you can see the ribs and the spine and everything, the parts of the image that are white are the dense bone parts, because those dense bony parts absorb the radiation. That radiation didn't get to the plate, and that's why those parts of the plates were still white. The black parts are where the X-rays struck it. Does everybody follow? All right, now, what I just described to you is a typical X-ray. And if you guys are probably aware, blood vessels don't show up on X-ray images. Most of the time, that's perfectly fine. We don't care. We're not looking for blood vessels anyway, but sometimes we do need to see the blood vessels. That's why we're here. That's why we're taking this X-ray image. We need to see the blood vessels. But blood vessels are neither thick nor dense. An X-ray photon has no trouble passing right through a blood vessel and making the screen dark. So what we have to do is we have to put something in that blood vessel during the X-ray procedure that will make it absorb the radiation. That is what would normally go in here. It's not part of the show. That was supposed to be done beforehand. But how we get those blood vessels to show up, we're going to inject this fluid into the patient during the actual X-ray. That liquid will block the radiation that is in the blood vessels, or block the radiation from passing through the blood vessels. So now the blood vessels will show up on the X-ray image, okay? Now what I just described to you is referred to as angiography. All right, angio means blood, ography means the viewing of, all right? So without contrast injectors, I just basically described the basic point of them, blood vessels rarely show up on X-ray images, certainly not in diagnostic capabilities, all right? Everybody clear? Any questions so far? All right, so that was the intro to the intro. All right, so like I said, angiography is a procedure performed to view blood vessels after injecting them with a radiopaque dye that outlines them on the X-ray image. This right here, this is actually a brain scan, and you can see how incredibly effective this fluid is. Some of these blood vessels here are thin as a hair. That's how little fluid they have into it. But if you can see them, that means they have contrast in them. Very effective. Next. Now, there's a whole bunch of different models of contrast injectors, but they can all be broken down into 3 kinds. There's CT, there's angio, and there's MR. Now, I tell all the students is all contrast injectors, they're like defibrillators and infusion pumps in the sense that you've seen one, you've seen them all. They all do the same thing the same way, basically, all right? But each one is going to have its own little bell or whistle or feature that's kind of unique to that model. So all CT injectors about 95% the same, and then each one's going to have its own little quirk about it. All right. Now there is something about CT injectors that makes them for CT. Same thing. There's angio injectors, and they have things that are made specifically for angiographic procedures. And then obviously the same thing with MR with that magnet. We have to have a special kind of special materials made to make that contrast injector, because that contrast injector is literally up in the patient, up in the magnetic field with the patient. So those are the three kinds. Wrong button. Still not far enough. So yeah, there's three kinds: X-ray or angio, CT, and then one for MRI. Now, each of the systems uses the injector to inject the contrast into the patient to improve, or in some cases make possible, the viewing of the images of the soft tissue. All right. Now there's, where are we at? Yep, the images produced are referred to as angiograms and angiographs. Now typically, how we get the fluid into the patient is going to be for CT and MRI injectors, it's an IV needle. For angiographic procedures, where it's the normal X-ray room, it's a catheter. And the catheter is very, very long, very thin tube, and they'll snake that catheter into the femoral artery or the femoral vein and go up into the different body parts in the heart with it, and they'll shoot the injection directly into that body part. Whereas for CT and MRI procedures, it's more, we're just putting the vein, catching the vein in the arm, we're just going to light the whole patient up and do it that way. Not quite that simple, but basically. All right. Is there any way to turn? Should have asked her when she was here. It's a little too bright. Nope, keep hitting the wrong button. Now, when it comes to contrast injectors, can we make it a little bit darker? Can we dim them a little bit? Yeah, thanks. Anyway, and it's been like this for a long time. When it comes to the manufacturers of contrast injectors, there's three big dogs, all right? And they're very much in a pecking order. First one, the biggest one by far is Medrad, Bayer Medrad. That one, they're probably 90% of all contrast injectors on the planet are made by that Bayer Medrad. They were Medrad forever, and then about 10 years ago, Bayer bought them out, and so now, but now everybody still refers to them as Medrad injectors. They'll make your most common types. They'll make the Mark 7s and the Provises. They'll make Stellants. They make the Spectra Solaris and the MR Experience. So they're by far the biggest ones. Wrong button again. Next one, the second biggest company, but in a distant second, is a company that changed their name pretty frequently now. I don't even have it up on here yet. It's a company called Guerbet, G-U-E-R-B-E-T. They're out of Cincinnati, Ohio, but they start off as Liebel-Florsheim, then became Mallinckrodt, then Tyco, or Covidien, then Tyco, and now it's Guerbet. They have their own CT contrast, CT, MRI, and angio injector type models. And then the third, and bringing up the rear, but there is a presence here, two companies, Bracco and EZM. They make your assists and your empowers. Appreciate it. Thank you much. Now the fluid, you can see here, this is an image of the heart, all right? And you see the heart in the background, and then this large, very well lit up artery right here. It's called the aorta. It's intravenous contrast is used to highlight the blood vessels, as we can see here. Once it's injected throughout the bloodstream, it circulates throughout the patient's body. Now that's one thing, it's nothing that we as BMEDs have to worry about, but you do have to keep in mind when they're using this fluid to take a shot of this particular vein or artery, it's on the living patient. And every time that heart beats, the blood in the vessels move. So we might fill this chamber up with contrast right here, right now, but we have literally like less than 1 second to pop that shot, because as soon as the heart beats, it moves. Heart beats again, it moves. So sometimes, like for CT procedures, they'll actually do that and they'll actually chase it. They'll inject just a small amount of contrast into the patient's body, and then just the CT system will track it as it moves throughout the body. And so it looks, when you get your image, it looks like one long shot, when it's actually, it was just chasing it. So we didn't have to fill the whole patient up. We just used this much and took images as it moved. Pretty wild. All right. Now, this bit right here, the X-ray, there's 3 different kinds of contrast injectors, CT, MRI, and angio. Now, 2 of them, pardon me, I'm sweating. I don't know why. 2 of them use X-rays to produce the images, CT and angio. The third one uses MRI, all right? So 2 different technologies are used by the 3 different kinds of injector model types. Now, angio and CT, the 2 that use X-rays to produce the images, the fluid, the magic ingredient in this syringe right here is iodine, all right? Something about the atomic structure of iodine. It has a number of electrons in its outer shell spinning around the nucleus that it blocks X-rays, okay? Iodine, short and simple, blocks X-rays. So the main ingredient in CT and angio injector syringes is iodine. So they're injecting that in the patient's blood vessels to block the radiation. Now, the other kind is MRI. MRI doesn't use X-rays to produce the images. It uses magnetic field and RF pulses. So iodine really has no effect at all on MR injectors, on MR pulses, or MR pulses and magnetic fields. So they have to use a different kind of fluid, and that different kind of fluid is called gadolinium. A gadolinium does for MR images what iodine does for CT and X-ray images. There is a long explanation. It gets deep. To really understand it, it gets deep. But basically, the thing in your body that makes the images, long story short, is the hydrogen atoms in your body. And gadolinium basically dampens the effect the impulses, the RF pulses on your body have on those hydrogen atoms. That's how it does it. Simple. I don't know why they didn't come up with it years ago. All right. Any questions so far? I know we haven't really got to the injector so much yet. Oh, and this is what I was just talking about. For X-ray and CT, iodine is used to produce the contrast fluids. And then right here for MRI, that is used, the agent is called gadolinium. Because basically it dampens the effect of the RF pulses on the water molecules, which are acting like the little antennas that produce the images. All right. Now, let's get to the actual machine a bit. Now the syringes, we do training on 12 different models. There's probably 17 models out in the world in use, and we do training on most of them. With just a couple exceptions, there's one thing that you have to know, the syringes. Every model of contrast injector has a syringe made specifically for it. So if you have a toolkit and you're the injector guy, you're gonna have a ton of these syringes because there's not just one syringe that you use for all your PMs, make model, doesn't matter. So every model has its own set of syringes, and they are one-time use only, okay? The syringe is used once and then thrown away, and that'll become an important thing later on. Now that's not for us. When we do the training, we send the students off back to the world to do their thing. We tell them, they know that these are one-time use only, but when you go back, first time you go do a PM on a stunt, that's what this one is, ask the department for a set of syringes. They literally use them once and throw them away. Their trash cans will be full of them. They have cases and cases of them. They shouldn't have no qualms giving you a brand new set. Those are now your PM syringes. You'll use those syringes or that syringe dozens and dozens of times before something happens to it, the tip breaks off or something, you can't use it anymore. But yeah, for PM procedures, we use the syringes over and over and over. All right. Oh yeah, and they're sterile. Not that we care about that. Embolism risk. Obviously, we're injecting fluid into a patient, so we're going to do that usually with an IV needle. It can be done with a catheter, but there's not really air embolization risk with a catheter so much. But the systems are set up so that whenever you fill the syringe up with a fill tube, this is my fill tube right here. Whenever we fill the syringe up, we always do it with the head pointing up. That way, if any air bubbles get in, they float to the top. And whenever we inject, it's always inject head down. That way, if any air bubbles did remain in the syringe somehow, they would float to the non-business end and not get injected into the patient. Now, some of these injectors, they do, well, I think all of them, but nobody ever uses them. Nobody ever uses them. There is a device on these contrast injectors that can sense when an air bubble is in the line, but they never ever use it. They never ever use it. And the reason for that is Like, if a normal patient is having an IV done or whatever, or getting injected with another fluid, not a contrast injector, if there's an air bubble, they don't obviously want that to get to the patient. So it will actually shut the system down. All right, the system stops, alarms go off, they come over, they can take care of everything, getting back going again. For contrast injectors, really no harm, no foul. For contrast injectors, they really don't want the injector to stop in the middle of a procedure, because if you think about it, we're in the X-ray department. The patient's on the table. What, other than this contrast fluid, what else is getting fired into this patient right now? Radiation. So if my injector stops, that means all the radiation we fired to the patient was for nothing. So that's total extra patient dose. So they really are very diligent about making sure there's all sorts of checks and balances and make sure there's no air bubbles in the syringe, because they really don't need it to shut down or abort the injection in the middle of the procedure. Yeah.
When you say people don't use it, do you mean it's a safety system that they turn off, or do you mean
it's an actual device?
Okay, so it's an
Yep.
external, like,
Exactly. Yep. Yep. Different manufacturers have different names, or don't know names for it, but it's basically the same, all of them. They put the IV needle in, and then there's this special, I think they're always clear. I've never seen one that wasn't cleared, like a clear bandage over the top of it that has little electrical wire leads in it. And those little electrical wire leads go into an EDS device, extravasation detection system box, somewhere in the room. What happens is, no, never mind. I'm thinking of extravasation. If the air bubble or if the IV needle is not in the patient's vein or artery, it will start to balloon up. That lifts up, breaks the connections between the wires, and that's how it knows. But that was for an extravasation. I got ahead of myself. Air bubbles. Yeah, same thing though. Same thing. They don't want to stop the injection in the middle of the injection. All right, so they're just very adamant about not making them, not using it. Like I said, every model has them. I've never in my life seen actually one on a machine when I was in the hospital. Not one time. So it's obviously not something that comes up much. Pressure limiting. Now, I need to tell you a bunch of stuff about other things before we get to pressure limiting, so this is my display, and I tried to lay the room out a little bit. I know people on the edges probably have a difficult time seeing here, but so this is my display. This is where the operator is going to punch in what the protocol is going to be. We're going to shoot this patient with this injection. All right. Now, every protocol has to have 3 things selected on it. All right. Now, there's more things that we can select, but there's 3 things that have to be selected. Everything else can be left zeros, but these 3 things have to have something. All right. One is flow rate, another is volume, and then the third is pressure limit, what we're talking about here. Now, flow rate, that's the speed of the injection. How fast are we shoving the fluid out of this syringe? Is it going to be 1 milliliter per second? Is it going to be 50 milliliters per second? That's the flow rate. The volume is the total amount of fluid we're going to fire into the patient. It's going to be 50 milliliters, 100 milliliters, 125. You get the point, right? Now, the third one, that's one that takes a little bit more explaining. It's an easy concept, but it takes a little bit to get there, right? Now, the third one is pressure limiting. Now, pressure limiting is a very important aspect of contrast injectors. What you do, a typical pressure limit is like 300 PSI, let's say, 300 pounds of pressure, all right? What we're saying is when we put that in the machine, this flow rate, this volume, this pressure limit, we're telling the machine don't exceed 300 pounds of pressure, and here's the important part, in the syringe, all right? This is not in the patient. 300 PSI does not get in the patient, all right? There's another kind of, this is a CT injector. It only goes up to 300, 325 PSI. Angio injectors go up to 1,000 or 1,200 PSI. 1,200 pounds of pressure in the syringe. That's how hard they want to shove this fluid out of here. Obviously, that is not to the patient. Whatever max pressure we have in the syringe here, by the time it gets out to this little tiny tube right here, we're getting single-digit pressures again. All right, it's just we don't want these to explode during the actual injection. All right, so what pressure limiting is let's say we do our injection, flow rate of 5, volume of 50, pressure limit 300 PSI. And for whatever reason, during the actual injection, the system is monitoring how much pressure is in each syringe, okay? If it senses that we have hit the pressure limit, if we hit 300 PSI, anybody have a guess? What does the injector do? No guesses? So yeah, set you up for failure. For comedic purposes, it does not shut down. All right.
Slow down.
It slows down. One of the things, the primary determinant of how much pressure gets built up inside a syringe is the flow rate, the speed of the injection. I mean, if you think about it, this is a 200 milliliter syringe. And if I selected 1 milliliter per second, it would take 200 seconds to shove all that fluid out of this little hole up here. That would build up no pressure inside the syringe at all. Let's say, and you can't do this, but let's say I could select 200 milliliters per second flow rate. That means all this fluid would get shoved out of this little tiny hole up here in 1 second. That would be a significant amount of pressure on the inner walls of this syringe during that actual injection. So that's what it's guarding against, that 300 PSI or whatever pressure limit we select, all right? We're telling the machine, when you hit 300 PSI, don't stop, because again, what else are we firing into the patient right now? X-rays. So if we're not gonna shut the injector off, how do we keep the pressure from inside the syringe from building more and more and more and more and more? We're just gonna slow the flow rate down. Now, here's the thing too. We selected a flow rate of 5.0 milliliters per second. All right, and all right, pressure limited. My injector slows down, but maybe it only slows down like 4.8 or 4.7. I mean, we're not saying it drops down to 1 milliliter per second. We might still be able to use these images. So that's another reason why they don't shut the injector off. All right, we're just gonna slow it down, see what we get. Maybe we're still good. All right, that's pressure limiting. Any questions? All right. Now, again, that's a concept, that pressure limiting concept, that is a misunderstood concept, even by the techs who use the machine. 300 PSI or 1,000 PSI, whatever you select. Again, that's only in the syringe. That is not in the patient. And also, it's not a goal. All right. If I select a flow rate of 5, I want a flow rate of 5 milliliters per second. If I select a volume of 50 milliliters, I want to shoot an entire 50 milliliters. If I select a pressure limit of 300 PSI, I don't care if we only got up to 10 PSI. We were just saying that's the max. Don't go over this. If we don't hit it, that's fine. Just don't go over this. So another little misconception about it sometimes. All right. Questions? Yes.
Is there a common pressure limit setting that they default to?
Yes. Typically for CT and MRI, it's 300 or 325 PSI, and that's pretty standard. And unless they're using like one of those IV needles that's actually more plastic than metal, they can't necessarily always go with that high of a pressure limit. If it's a metal needle, metal IV needles are rated at 400 PSI. So if they're using a metal needle, they should just, for CT and MR injectors, just set the pressure limit as high as you can make it, 300, 325. Angio injectors are a little bit different. Angio injectors, the pressure limit will be higher because angio injectors can shoot higher flow rates, but I don't want to get too much into the weeds, but different size catheters, because in angio, there's all different lengths and sizes of catheters. That catheter determines what the pressure limit needs to be, because that's the weak link. That's what we don't want rupturing. So yeah, for angio injectors, there is not one standard pressure that's the most commonly used. It changes every shot based on the catheter they're using. Another questions? How are we doing on time? You are kidding me. We're not even halfway there. No, we are. This is gonna be rough. Strap on. All right. I talked about all that. Still more. I told you this was a long discussion. Now there's different. The configuration of your contrast injector is basically, where's the head? Is it on a pedestal? Is it on a table? Is it on a wall? Is it hanging from the ceiling? All those are mounts. Pedestal mount, table mount, ceiling mount, wall mount. All in one is when the whole thing's on one cart, which the Stellant doesn't do that, but some models do. We talked about the syringe. Now the syringe heaters, one of the things we spoke about pressure limiting. One of the other things that affects how much pressure gets built up in the syringe is the viscosity of the fluid. Now this fluid, the contrast fluid, it is close to water, but there is a slight syrupy texture to it. There's a little bit of thickness to it. So one of the things that does affect the pressure in the syringe is how thick the fluid is. So what they want to do, they want to keep the fluid, the contrast fluid, the syrupy fluid, as warm as they can. What that does is that makes it thinner, less viscosity, so it flows more easily. So that's what these are. These are just heaters you plug in. They're set to 37 degrees Celsius, which is 98 degrees Fahrenheit body temperature. And they're basically digital. They work or they don't work. There aren't adjustments for them. When they break, you throw them away. and they're freakishly expensive. This is it. This piece, the wire with the plastic and the hard cover right here. Guess how much? More. He said $1,200. $1,300. I'll bet they could sell them for $6,000. They still have to get it. They do, and they break a lot, and they're throwaway. So 1,300. All right, armed lights and indicators. So whenever we do an injection, so this right here, reset, yes. So phase A, all right, so on my syringe here, on my injector here, I have contrast syringe and a saline syringe. Saline is just basically saltwater. Contrast is the magic fluid, right? Now, my injectors, I can select multiple shots for each injection, all right? They're referred to as phases. Now, if we look here, I know it's gonna be hard to see for some, but my two syringes here, the green one is contrast, the blue one is saline, that's my A and B syringe. Now this first row right here where it says it's in green, it's 1 and 1. The green means it's contrast, my green syringe. And I'm gonna select my flow rate here, we'll say 5, and my volume here, we'll say 20. Enter. Then down here, I can select a second phase, all right? So this would make it a 2-phase injection. And I can select contrast A, contrast B, a mixture of the two. I can also select pause and hold. Talk about that in a minute. So let's go the different fluid, 5, 20, enter. So there, we have a 2-phase injection, all right? So that's 2 injections, but one click of the button, we can send them both. So each one, my first phase is green, flow rate of 5, a volume of 20. Second phase is gonna be the blue fluid. They're both clear, but the blue side, which is the water, the saline, flow rate of 5 and 20. So while this is a 1 injection, it's a 2-phase injection. So I'm going to lock the protocol so it can't be changed, and then arm the button. And then whenever they go to arm the injector, this is that moment I was talking about earlier, they have to tell the system, they have to tell the injector that they have checked for air. All right, so there's always a reminder when you go to arm the injection, meaning we're getting ready to shoot it. Arm the injector, window pops up in some form or another saying, have you checked for air? They have to hit yes. Now, the manufacturer is no longer liable if they kill a patient with an air bubble because they said they did it. All right, so we brought all this on. The armed indicator light. These right here, these are your visuals. These are the visuals to the operators. We're armed and we're ready to go. All right. Now, I also said that whenever you inject, you have to tilt the injector head down. All right. So it's head up to fill it, head down to shoot it. But you notice on this model, and this is probably the most technologically advanced model of contrast injectors out there. But one feature it does not have that a lot of other contrast injectors do is it doesn't sense its head tilt position. A lot of the new injectors now, it can sense its head tilt. And if it's not tilted below horizontal, it won't let the operator arm the injector. Most injectors do that, but this one, the most sophisticated one, this one does a ton of things others don't do, but that's one common thing that it does not do. So these are your armed indicator lights. It's telling the operator when you hit the start button, we're gonna shoot. And then red is abort, yellow is start and pause. So we'll start the injection. First contrast, flow rate of 5, a volume of 20. Then it automatically moves over to the next one. All right, 2 shots, 1 protocol. So that's a 2-phase injection. These injectors, some of them go up to 4, 6, even 8 phases. I've never seen that long of a shot, but yeah, some of them will go through up to 8 different phases on that. Now, when you're changing a phase, you're either changing the fluid. You want to go from contrast to saline or vice versa, or you want to stay with the same fluid, but you need to change the flow rate. All right, so each one of those would require a new phase. The enable buttons, what this is for filling the syringe up. Like I said, if we have a bottle of contrast, we're gonna throw our fill needle there, and to be honest, these buttons right here, these are my forward and reverse buttons. Every injector has some version of these. Forward and reverse buttons, that's to load the syringe, fill the syringe with the contrast and the saline. But if you'll notice that these forward buttons don't work until we hit an enable button, which is the middle button. It lights up, that's telling the operator, all right, if you hit a switch now, your syringes are going to move. And the reason they do that is they don't want an accidental push or pull of the syringe while it's actually connected to a patient. Just the injector or the operator grabbing it. So if you hit one of these buttons, the first thing that has to be done is telling it to enable. So we hit that, and then that's how we electronically move the buttons forward and reverse. Same thing, variable speed, and then manual knobs down here. You can do the same thing if I just want to move it 1 or 2 milliliters. All right. We already talked about these. There's 3 things that the operator has to select before we can actually do a shot: flow rate, volume, pressure limits. Now these protocols, they're stored in memory. Every injector has a memory portal. Though, I mean, a typical hospital will have 4 to 6, maybe 8 protocols stored in memory. They can all hold like 100 or something, but they don't hold that many protocols. But typically what they'll do is they don't sit there when the patient comes in for, you know, an AP chest, you know, anterior, posterior chest through the front, out the back. They don't like sit there and, well, let's do this flow rate. No, they have an AP protocol. They just go in memory, click one button, it brings up the entire protocol, whatever it is. That's what they use. They typically stick to those library protocols. I'll deviate them a little bit sometimes for the size of the patient, but they typically stick to that. They rarely like enter the protocol for each patient manually. A multi-phase or multi-level injection, that's what I demonstrated when I showed phase 1 and phase 2, and they can go up to 4 or 6 or 8 phases. The term there, multi-level, there's one company, and it's MedRad, it's the big company. For one of their machines, they don't call them phases, they call them levels. So, but it's the most common injector out there, so we have to throw that in. But that was what I demonstrated earlier. Now, a hold and a pause. So let's say we have a multi-level or multi-level injection, a 2-phase injection. But between phase 1 and 2, I don't want the injector to automatically go to phase 2 when it's done with phase 1. For whatever reason, I want it to chill for a second. All right. Now there's 2 chills. All right. There's hold and there's pause, and they're not the same thing. A pause is for a predetermined length of time. So you'll put in phase 1. I don't know if everybody can see this, but so for phase 2 here, we'll put in a pause for 5 seconds. And then phase 3, we'll go back to flush 5. There we go. All right, so on this one, we're gonna get a 5-second pause. We're gonna arm, lock, arm. Be good. Yes. What didn't happen? Arm. Hit the wrong button. There we go. All right, now, when we do this injection, shoots contrast, then there's gonna be a 5-second pause. And without the operator intervening, the injector takes over on itself, all right? And then the injection is finished. Now, a hold is same concept, but it's an indefinite stoppage. Instead of a pause, we put in a hold, and then what will happen is now the injector will get to the hold phase, and it will hold the injector, and it won't restart until the operator hits the inject switch. That is the subtle but different aspect of a hold versus a pause. All right, about done. Program delays, there's 2 kinds of delays. They go by 3 different names. Now remember, this is working in conjunction with the imaging system. So you have your imaging system and your contrast injector. An inject delay means that I'm gonna start both the imaging system and the injector together, but there'll be like a 2-second delay with me actually hitting the switch before it actually starts injecting. And the opposite is exactly the same, but that's called a scan delay or X-ray delay, where I'm going to shoot both of them, start both of them at the same time. My injector will immediately start injecting, but for whatever reason, we don't want the imaging system to start imaging that moment. We want to pause that 1, 2, or 3 seconds, and then it will start injecting. So those are the 2 different kinds of delays, but they go by 3 different names: inject delay, scan delay, X-ray delay. KVO, that's a feature. Not a whole lot of injectors have it, but that's a feature if you're an infusion pump person, you're familiar with KVO. Keep vein open. What that does is every so many seconds, the injector will just do a little drop of fluid out the IV needle just to keep the tip of the IV needle from developing a blood clot or the vein from clotting. And then test injectors, what I was talking about earlier. When the patient is in the room, especially CT and MR, they're in the room by themselves. So they don't want to IV the patient and then leave the room and find out the needle missed. So for phase 1, a lot of contrast injector models will actually do a test inject. It's a very small volume, very slow volume, very small volume, very slow flow rate. And it's just going to see if the arm bubbles up during the actual injection. So the operator is actually standing next to the patient while they're doing this. Then in the exam room, once we're good, they leave the room, go back to the control room, and complete the injection from that vantage point. All right.